Okay, perfect. So we're going to start again because we haven't recorded the first part. So today we're going to talk about PyTorch, basically. And PyTorch is basically a library that is useful for two important things. One of them is for doing computation on tensors and on GPU, and it's very, very similar to what NumPy does. And we'll see what, for example, functions we're having and how they're similar to it. And the other important thing that most people know PyTorch with is its ability to actually implement neural networks. It has a lot of functionalities, such as automatic gradient calculation, that can be used for neural networks as well. So basically, what is a tensor? Because we're going to talk about it a lot today. Tensor is basically a multidimensional array. And today we're going to see how we can actually use what happened? Oh, yeah. So yeah, today we're going to learn how we can actually use PyTorch in order to do the computations on tensors. So we can think about PyTorch as being a more powerful replacement of NumPy. It's mostly for like doing computations and doing calculations on GPU. And the other important thing that PyTorch does that we probably is more interested in is its ability and its functionalities for implementing a neural network. So today we're mostly gonna focus on Torch, torch.autograd, and torch.nn. Torch itself is, again, a library very similar to NumPy, but for tensors and GPU. Torch.autograd is a library for finding the gradients instead of us kind of implementing it from the scratch. And finally, torch.nn is a library that has like a lot of utility functionalities for implementing neural networks. So if you want to use Google Colab, you don't need to install PyTorch. It is coming pre-installed on Google Colab. But if you're working on your local machine, you might need to actually install PyTorch. You can use the link that is here. And basically what happens is that you just choose these options, like your like operating system and everything, and then just run this code that it generates on your terminal. So today we're going to just use two other utility functions for making the prints more beautiful. So ice cream is basically a more kind of fancy version of printing, and Torch summary is also a very important library, very useful library that helps us to print the neural network architectures. And these are the libraries that we're using. Mostly today we're going to focus on Torch, torch.nn, and also the autograd library. So if you want to check your PyTorch version, you can just print it's like torch.2 dashes version 2 dashes. So it will look like this. So it basically, the way you should read it is it's version 2.5, and it is running on CUDA 12.1. So this is how you should be actually reading it. And CUDA is a library, it's a helpful library to kind of manipulate and do the calculations on GPU. So since PyTorch is doing the calculations on GPU, it kind of needs this CUDA as some sort of interference interface to talk to the GPU. So to see if you have a GPU on your device, probably if you're using a laptop, you do have it. And if you're connected to Google runtime, you should also be having it. You just run this command, the nvidia.smi. It basically tells us we have a Tesla T4 GPU. So Tesla T4 GPU is a relatively powerful GPU, more powerful than your laptop and computers. And it costs around $1,000, but you have it for free for a limited time on Google Colab. And now that we have this introduction, we can start with what is PyTorch, how we can actually use it. So the first step we will do is obviously starting by defining two tensors on PyTorch. So as I said, PyTorch has the ability to also work with GPUs. So we're gonna just define one tensor on the CPU and the other tensor on the GPU. To do this, there is an argument, there is like an input argument called device. You can either set it to CPU or you can set it to CUDA to kind of show which device you want your tensor to be actually on. Here I have, for example, the same tensor, one time on CPU, one time on GPU. And I will use this kind of ice cream library to print it. As you can see, they are the same thing. So I used torch.zeros. So torch.zeros is the same thing as numpy.zeros. It creates like, let's say, matrix of all zeros with the dimension that we're giving it. So this is what I'm having. So it's 1 by 2 by 3. And this is how actually it looks like. So the other thing that is very, very important is how we can actually move one tensor from one device to another, because as I said, you cannot add or multiply or do any calculations on two tensors that are not on the same device because of the way that the computer architecture works. So if you want to do, for example, if you want to add one tensor that is on your CPU to a tensor that is on your GPU, you should bring both to the same device. If you have a GPU, it is a better idea to do all your calculations on your GPU. So what you can do here, for example, is that I have this tensor with zeros, and I'm going to create a tensor on my GPU, which is the same thing. So basically, I'm going to move my tensor from CPU to GPU. So now we can just check and see that my tensor is on GPU. So by default, if you don't specify a device for it, it is going to be on your CPU. So here we can see when we're printing it, if it's on CPU, it doesn't tell you. So now let's continue with the part that is also new for the class. So we talked about Python like lists and how we can actually convert them. So like realistically, most of the time, you're not going to define an all zero kind of tensor. You have a data set that is in form of lists or arrays, and you want to convert it to a torch tensor. So the way to do it is very simple. There is a very important functionality, torch.tensor, which converts anything that is in the inputs to a tensor. So basically, we have this list. We input it once as it is, as a list. And the next time, we're inputting it as a NumPy array. So we first convert it to a NumPy array, and then input it to our like torch.tensor. And finally, we have another command, which is from NumPy, which is used for converting NumPy array to tensors. So at the first look, both of them are the same thing. They're just converting a NumPy array into a tensor. But we're going to see how they actually differ from each other. So if I run this cell, you can see that all of them are now tensors. All of them are the same thing. So now let's see why we even have a torch.from NumPy. What purpose it's actually serving when we have already torch.tensor. So the difference between them is how they are actually connected to the memory. So basically, if you have a torch.tensor, if you input a NumPy array to it, it will be converted, and then it will be stored in a separate space in your memory. So if you change your original NumPy array, your tensor won't be changed. But if you use from NumPy, basically what happens is that it only kind of stores the location of the NumPy array in the memory. And every time that you're calling that tensor, it goes to that location and converts whatever is there to the tensor. So for a very simple demonstration here, we had a like Python list, our old 1, 2, 3. And then after we're converting everything to PyTorch, one time using torch.tensor, which is our version 1, and one time using torch.from NumPy, which is our version 2, we are going to change the first element of the NumPy array. We're going to replace 1 with 100. And let's see what happens for the tensors. So you see the NumPy array has changed to 100 to 3, but the tensor, the torch.tensor output is still 1, 2, 3, because after using torch.tensor, they are kind of disconnected from each other. But if you're using the torch from NumPy, your version 2, which is created using that from NumPy, is now actually the same thing as your new NumPy arrays, 100 to 3. So this is the difference between them. So be very careful with these. If you're debugging your code, if you, for example, loaded, let's say, a data set, and then for some reason you change the data set at the downstream of your code, and you don't want it to be changed in your, let's say, PyTorch or like your tensor, please use torch.tensor, otherwise use torch.from NumPy. So with this, now let's see how we can actually train a very simple model. So we start with the logistic regression. You're familiar with logistic regression. And we're creating a very simple data set. So this is my toy dummy data set. So again, the data set looks like this. So my features are from 0 to 10. If that feature is bigger than 5, it's going to be labeled 1. Otherwise, it's going to be labeled 0. So if I want to plot it, it will look like this. Okay, so it's a very simple, very kind of like stupid, simple data set, but this is just for the demonstration purposes. So what I'm gonna do is I'm gonna create this logistic regression model. So for a logistic regression model, first of all, we need to have a weight matrix and a bias vector. So we're gonna multiply the weight matrix in the features and then add it to bias. So we call it the logits of our like logistic regression function. So it's basically just multiplying X with W, adding it to B. And then we are going to apply a sigmoid function on these logits to get the prediction, okay? So these predictions are basically the probabilities. So the next thing that we need to do is we need to kind of convert them to 0 and 1s. We use a threshold of 0.5. So if the probability is bigger than 0.5, it's going to be 1. If it's less than that, it's going to be 0. And if it's 0.5, it's going to be 0. So if I kind of like print everything that is here and find the accuracy, it will look like this. Okay, so you see the labels that I'm having. So nothing is trained here, okay? So I just had an all 0 weight and an all 0 bias, okay? So I have like this W and B defined here. You see everything is 0. So naturally, if you multiply it by your features and add it to the bias, it will still be 0. So I had a bunch of zeros. I found the sigmoid of 0. So the sigmoid of 0 is 0.5, if your X is 0. And then because of the way I kind of threshold it, it's gonna be all zeros, okay? So this is not a very good like classifier. I'm getting a 0.54, but it's basically useless because it predicts everything to be 0. Nothing is trained right now. So now let's train this model, okay? So how do you train it? We can use, for example, yes. So the long, yeah. So basically here, the long here is basically converting everything to a float, okay? Yeah. So it's nothing like very important. And yeah. So we want to now train this model. How can we do it? You've learned it in the class. We can use, for example, gradient descent and update the parameters using gradient descent. So for gradient descent, we need to have the gradients of our weight and also our bias. So I'm just going to create them, and the gradient of weight and bias is going to have the same shape as weight and bias. So just like NumPy, where we had a zeros-like function, we have the same thing in Torch. So if I call torch.zeros-like, it's going to be basically an all 0 matrix with the same shape as my W matrix. And we also need to define a loss function. So a good loss function here is going to be the BCE loss, okay? Binary cross entropy loss. It looks like this. It's minus a y times the log of prediction plus 1 minus y times log of 1 minus prediction. So basically, if your y is 1 and your prediction is 0, one of the terms goes to 0, the other one goes to 1. So basically, they get 0 if they're not matching. But if they match each other, they are going, yeah, no, completely the opposite. So if they are basically matching each other, like if your prediction matches your real y, one of them goes to, like both of them goes to 0, otherwise one of them won't go to 0. So if your prediction doesn't match your original value, your ground truth value, you are going to increase the error. And what we need to do is we basically need to find the gradient of this loss, this BCE loss, with respect to my W and B. Then calculate a forward pass, then update the parameters based on the gradient, and do this in enough number of epochs so that your model is trained. So, okay, so let's do this. So for this part, we are going to kind of find these or calculate these gradients on our own. We don't use like a function, but as we talked a little bit about it at the beginning stages, there is a library called torch.autograd. So it automatically finds the gradient for you. So you don't need to find any gradient when you're implementing, let's say, a logistic regression model or a neural network. Here, we just want to show how it's working. So if you take the gradient on your paper, like write everything down, you will know that the gradient of W is going to be X times prediction minus Y transpose. And then your B is going to be the mean value of your prediction minus Y. So if I create them. So they will just look like this. So you see, these are the gradients of my first step. Okay, so I created these W and B. I multiplied them inside my input, and then I found the gradient for them. So that's just the first step. So the next step is now I need to update my parameters based on this gradient. Again, a very simple gradient descent. I need to have a learning rate. So here my learning rate is, for example, 0.001, whatever learning rate is going to be okay here probably. And then I'm just going to update my weights. So I find a gradient, multiply it, update it. You're pretty much familiar with it at this point. And you see, so at the beginning, my W and B was 0. So this is the way I initialized it, okay? But then after one step, you see, I have a different value. So it means my model is getting trained, okay? So since these are not equal to each other, we can kind of verify that the gradient is actually applied. So if I put all of that in one place and just summarize it, we first of all created the W and B. So what was the goal? The goal was we had a data set. We wanted to train a logistic regression model on it. So we initialized them with 0 vectors and 0 matrices. So W is just like a 0 matrix and B is just like a 0 vector. And again, I had just one feature. So it's just 1, 1. And then I defined like the forward pass. Okay, so here, to calculate the prediction, it's just going to be the sigmoid of my W, like W transpose times X plus B. It's just like how like the logistic regression model is working. And then I'm gonna threshold the probabilities based on 0.5. If it's bigger than 0.5, it's going to be 1. If it is equal or less than 0.5, it's going to be 0. And finally, I can find the accuracy very simply. Just check if the predicted, let's say, vector is the same as my original ground truth vector. So the next thing that I did was I tried to kind of train this model, because if you just apply this, you just get zeros. So to train it, you need to find the gradient. Here you see I kind of calculated the closed form formula for the gradient. I literally like calculated what will happen using calculus if we take the gradients. But you will see in many cases, finding the gradient is not that easy, and it's also not numerically stable. So the PyTorch autograd function will automatically do this part for you, okay? So you don't need to implement any gradient if you're using PyTorch. And then I just did this training. So this is just one epoch. So it just got like updated once, but it's probably going to be better. So yeah, you see here at the beginning we had this accuracy, and then this was our like gradients. So if we apply the gradient using that 0.001 learning rate, we're going to get the same thing. You can just calculate it yourself. If my learning rate was higher, then the value for the next step would be larger. If the value is too small for you, it's maybe because of the learning rate. So this is a very kind of common step in any algorithm that is trained with the gradient descent, but we can actually use PyTorch. So to compare these together, I'm going to create a function based on all of these steps, and then I'm going to compare this function with the output of PyTorch to show that it's the same thing, okay? So these functions are basically the same things as I talked about. I just put them in the kind of function form. So the first step we did, if you remember, we initialized everything with 0. So I create a function, call it init params, that kind of initialize your parameters. Then I have this compute prediction, which is basically your forward pass. So it just multiplies X with W and then add it to B, with our W transpose and add it to B, and then pass it through a sigmoid. I have the get labels, which kind of looks at these probabilities, these output probabilities, and convert them to 0 and 1s. I had this compute accuracy, which just computed the accuracy, compared the ground truth value with the prediction values. And finally, I had the compute gradient and apply gradient. So compute gradient, just you input X, Y, W, and B to it, and you will get the gradient with respect to W and gradient with respect to B. And then we had this apply grad step, which was your optimizer step, okay? This was the step that you kind of apply your like changes to your parameters. So if I kind of write it in a function form, now I can easily run a training loop on it. So let's see here. Yeah. So basically, I choose the learning rate to be a little bit larger than the previous time because the previous time it was too small. So I just put it as 0.01. I initialize my W and B. So I create these, like basically, if I call this function, it will give me a W and B. And finally, I'm gonna just track this like accuracy and the loss during my training. So what you do in training, first of all, you use your, for example, initialized model to do a prediction. This prediction is probably not good. It's a naive prediction. Your model is not yet trained. Then just for for the sake of just tracking the accuracy, I'm going to save it here. And then the next thing that I'm going to do is I'm going to find the gradient of my, let's say, W and B, my loss function with respect to W and B. So here I use the BC loss function, so the gradients were like the one that I kind of implemented there. And then I just find the loss function just for saving it and then apply the gradient to it. And let's see how it looks like, okay? So for this, I'm gonna plot like each step at like every 10 step, I'm gonna like do this plotting thing. And then I'm just gonna see how the accuracy will improve. So ideally, I want the accuracy to improve. This is how the model is getting trained. And if I run it, it will look like this. So you see, it started with 0.5, which was the naive prediction. Everything was 0. And as it's kind of trained, you're getting above 90%, which is not that strange given the data set was a very simple one. So this is how we can actually train a logistic regression model. I think we implemented it in your first assignment, so you probably are familiar with like all these steps. But the thing is, this is a very common thing to do. So people created a library for that. And you can actually use PyTorch libraries for this. So if you kind of import these functional sublibraries, the functional sublibrary includes a lot of utility functions, like, for example, all the loss functions that you might need, all the activation functions you might need. And then what you can do is you can just use that. So here, for example, we defined our loss function, the BCE loss function like this. But instead of that, we could just call the f.binary cross entropy, okay? So you don't need, you can just like go to, like, it's not only the binary cross entropy, you can just go to this link. Let's go to PyTorch loss functions. And here you can see like a full list of all the loss functions that you're having in PyTorch, okay? So you don't need to really implement anything. So you just call it from the torch functional or from the NN directly. So let's see if they're like close to each other or not. Obviously they should be because that's what we expect. So I'm just gonna use this assert torch is close. So if they weren't close, it would raise an error, okay? So now it didn't raise an error, so it means that both loss functions are almost the same thing, okay? So now let's see if we can kind of replace everything with their PyTorch counterparts. So remember, we used to calculate the compute grade, like compute prediction, the forward pass. But what we can do now is we can actually, where is it? Okay, so yeah. So let's just quickly go over all of them again, just to refresh your mind. So we used we calculated the prediction by multiplying them and then running it through a sigmoid. We calculated the the other version, like the other thing that we can do is we can use PyTorch for it. So there is a concept called a linear layer, okay? So what a linear layer does is the same thing as what this kind of multiplication does here. It multiplies your weight in your inputs, the input to that layer, and then it adds a bias vector to it. So instead of us writing this kind of, let's say, calculation like this, you can just say, okay, I'm defining a linear layer with the weight W and bias B, sorry, W transpose and bias B. And then I'm going to kind of pass the output of this linear layer through a sigmoid. So that's how my forward pass will look like. So again, just to see if they are the same thing or not, I'm just gonna see if they are kind of the same thing. And as you can see, if they weren't the same thing, so again, the reason I did it like this, and this is good to know because this is the way we define the test cases for you. So since you have two vectors, there is no way to kind of see if the two vectors are equal to each other or not. If all the elements are equal to each other, that would be great. But the problem with like computers is that you always have some sort of numerical like errors, although it's very, very, very small. But that makes equality sometimes like not that good. So what we usually do is if you kind of subtract two very close numbers to each other, despite that, like even if they are not kind of like 100% the same thing, and they have a very, very small error, it will go to zero, okay? So if you subtract them, you will get zero. So all of your kind of values should be zero. So what I'm gonna do here is that I'm gonna kind of find a new kind of output, a new prediction output, that is the subtraction of these two, and then see if the maximum value of that output is zero or not. Basically, it means all the values are zero or not. So this is one way to check if, for example, two arrays are the same thing or not. And if you use this assert, and you probably see it if you are submitting a wrong thing on Gradescope, it basically raises an error that these two aren't equal to each other. It expected something else, but got something else. So now let's do the same thing. So now let's replace the compute gradient that we kind of wrote with the PyTorch version. So the compute gradient we wrote was it find a forward pass, and then it just found using the formula that I actually found, the closed form formula, the gradient. But what I can do is I can actually use PyTorch. So this is very important. This is probably one of the most important things today. Instead of defining the gradients yourself, you can use dot backward in PyTorch, okay? So if you have a loss function, so my loss function is my entropy, and I want to take the gradients of my parameter, like this loss function, with respect to my parameters. So if I call loss.backward, it automatically gets these gradients and save them in a .grad kind of like object. So we usually call this like a gradient taped. So basically whatever kind of array, whatever parameter you have, if you call loss.backward, it calculates automatically the gradient for it, and then it attaches it, it tapes it to that variable, okay? So if you call loss.backward, you can have access to the gradient of every parameter in your model. So here we just had a W and B, but you can imagine for deep neural networks, you have a lot of parameters, you have a lot of layers. So you cannot really keep track of them and like do much, like, and you cannot like really find, it's not actually very accurate to find a gradient by hand for each of the layers, for each of the parameters. So if you use PyTorch, you're kind of having this peace of mind that all the gradients are calculated and you can access them by calling the .grad object, okay? So all you need to do is to call this loss.backward. What loss.backward does is that it calculates the gradients and then attaches them, tapes them to your original variable. And if you want to access them, you just call that variable, that parameter that you're looking for, .grad. So let's see if they are equal to each other or not. What happened? Okay. And supported. And B minus DW. Okay, it's very strange. Didn't have. Oh, yeah, that's correct. Yes, thanks. Okay, so you see here I have the gradient of both W and B, and I'm just going to compare them to see if they are equal or not. Again, since there might be numerically like different, like a very, very small precision, I'm going to use this epsilon. So if it's like, if the difference between them is less than this number, which is a very small number, they're almost the same thing. And if I do it, you see, I'll get them to be the same thing. So I don't get an error. And just to show you, I'm gonna just print this. So this is the difference between the like W's, the gradient of the W's between the function that I created and also the function that PyTorch has, so like the autograph that PyTorch has. So you see the difference is very small. It's like 0.00000001, which is kind of nothing in the grand scheme of things. And that's how you can actually find this difference. So instead of me using my own functions, now I want to use PyTorch functions. And this is the way you should be doing, except we ask you to implement it yourself. So if you want to, I don't know, use it for your research project, for like a competition or something, you can use this sort of like idea, this sort of training loop. And again, we didn't get into neural nets yet, but you will see the procedure is very, very similar, okay? So the concept of training with PyTorch that I'm gonna describe here is the same for every model that we're gonna see. So first of all, since it's a gradient-based algorithm, we need to have a learning rate, and then we need to do some initialization. So here we initialize all the parameters by 0. In some cases, this initialization is not good, okay? So you need to initialize with a non-zero value. There are so many different initialization techniques out there. And if you have a convex loss function, what is a convex loss function? Is, for example, let's say MSE error. So it is convex, it is like this, okay? This is your loss. So doesn't matter where do you start, whenever you're starting from any point, and as long as you're kind of training for enough number of epochs, you will end up at your like global optimum point, okay? But the loss function for, like, for example, a neural network, it's not convex like this. So you might get a loss function that looks like this. So we know that this is, for example, the most optimal kind of point that you want to reach. But if you start, let's say, from here, you will probably end up at this local minimum, okay? And then there is no way for you to get out. So the initialization, if your loss function is not a convex function, can actually be very, very important, because depending on how you initialize, you might get to a not very good optimum point. So there are so many different kind of strategies for initialization. It's actually a very like active research topic. Usually people do, for example, like initialization using a normal Gaussian function. But there are, if I will actually show you after we cover the neural network, there are some very specific initializations, some very specific distributions for initializing, so that it will kind of capture this optimum point as much as it can. So let's start the training. So again, the training loop is very similar to the function that we implemented together. So the first thing I'm doing is I'm doing a forward pass. So I'm calculating the predictions using the untrained model. So at the beginning of the epoch, we use the model from the previous epoch to do the prediction. Then again, this accuracy is just for us to see if the model is getting trained or not. If you are not interested in keeping track of accuracy, you don't really need to calculate it here. The next important step is calculating the gradient. So first of all, we found the forward pass, we found the prediction, and then we need to calculate the gradient. So when you're calculating the gradient, automatically you're finding the loss function at the beginning, and then you're finding the gradient of your parameters with respect to that loss function, okay? So, and finally, the last step is I'm gonna apply those gradients. So basically, I'm gonna do my optimization here. So again, if this is, for example, the gradient descent algorithm, you're just having original parameters minus learning rate times your gradient. And let's run this, see what happens. So this time I'm gonna plot loss, not the accuracy. And as you can see, the loss is kind of going down. This is what we like usually, okay? So we like the loss to go down. And you see, this still has potential to go even, like become even better, because we usually continue the training until the loss kind of plateaus, okay? It becomes like a straight line. So this was kind of like what we had. And now let's even make it one level kind of more high level. So if you remember, we kind of created that gradient descent function on our own. So we used the PyTorch here. So where was it? The compute gradient function, for example. So we kind of used PyTorch, but still we had to kind of create this compute grad function. So we can make this even automatically with PyTorch. So this that you can see here is now one level more kind of in the hands of PyTorch. So you have less kind of control over it. PyTorch does it for you now. So what I'm going to do here is this. If you want to calculate your gradients using PyTorch, you don't want to calculate your gradient yourself, you need to also set these to true, okay? So what does this line doing? So when you put w.requiresGrad true, what it does is basically it tells PyTorch that I need gradient for this parameter, okay? So when you are doing the backward, this is what I need, okay? So if you have a parameter in your model that you don't want to train it, you don't need the gradient for it, okay? So you should set this to false because like I will show you how the code will look like now, but in this kind of version, what PyTorch does is that it automatically finds all the gradient and it automatically kind of, let's say, optimizes all the gradient, all the like the parameters using the gradient, okay? So if you want to have a fixed parameter, if you don't want to train a parameter, if you want to freeze a parameter, you should set the required grad to false, okay? This way you are kind of telling PyTorch that, okay, this parameter, I don't want it to be trained. So let's do it and see how it looks like. So instead of me defining the kind of formula for updating, I can use PyTorch optimizers. So there is a sub-library called torch.optim. You're familiar with gradient descent, stochastic gradient descent, but there are so many other algorithms, like for example, Atom optimizer that are used these days. For example, they have adaptive learning rates. They all have some sort of like functionality to make your training smoother. So here we just use the stochastic gradient descent and just have W and B as our parameters. So this is important. Here we put W and B, but you can also put, I will show you, for example, for neural networks, for example, model.parameters. That means a list of all of the like trainable parameters of the model. And then we need to specify the learning rate. So here, for example, the learning rate is 0.01. And finally, the last thing I'm going to do here is it's going to be very similar to the previous case. I'm going to find a prediction, but this is the part that is different. So this is the new part. So I want to do the optimization by PyTorch, not that function that uses PyTorch. So first thing I need to do is I need to reset my optimizer. And this is a step that people forget because it's a little bit counterintuitive. You expect PyTorch to do that, but by default, PyTorch kind of accumulates the gradients at each epoch. So if you want to apply the gradient of that epoch, which is what we want to do in stochastic gradient descent, to your loss function and to optimize it, what you need to do is you need to use the zero grad. So this line basically tells your optimizer to remove all the gradient you have, remove all the memory that you have, and then you find the loss function, which is, for example, the binary loss function here, and then you call the backward. So what happens here? So right now, the optimizer doesn't have anything in the memory. You found the loss function, and you found the gradient of all of the parameters with respect to that loss function. So now we want to update the parameters. So to update it, you need to call optimizer.step. Okay, so you call optimizer.step, and it will automatically update all the parameters. So here you see I didn't put anything about W, anything about B. Doesn't matter. Whatever parameter you have, as long as you're finding the backward for it, it will also update it. If you don't want to update a certain parameter again, you need to set the required grad to false. And again, I'm gonna just show you the loss function. It's gonna be the same thing probably as before. So the important thing, I mean, if you learn this today, you're gonna learn PyTorch. Basically, you don't learn anything more about it, is how you can actually train a model in PyTorch. This is the logic. This is how PyTorch kind of trains your model. So first step, you need to create your model, or you need to initialize your model. Here, our model just had W and B. Then you need to create your optimizer, okay? So here my optimizer was the SGD optimizer, a stochastic gradient descent optimizer. And this optimizer has some input values, for example, the learning rates. You can specify the learning rate, but by default, all of them has a default like value. And then you need to do the training loop. So how does the training loop looks like? First of all, you find the forward pass, you find the predictions, and then so it's kind of up to you. So you can do this first or the next one first. I also here reset the optimizer, set it to 0 grad, or you can do it after finding the loss. Yes. So because by default, that's a little bit counterintuitive, but by default, at every step, PyTorch does not remove the gradient. It adds the new gradient to the previous gradient, okay? So it keeps kind of growing. If you want to use, for example, SGD, you don't want this to happen. You use the gradient at that step. So you just use the 0 grad, and then you find the loss function, and then you compute the gradient. So how you compute the gradient using loss.backward. Loss.backward means the gradient of all the parameters, gradient of loss with respect to all the parameters. And finally, you use optimizer as a step. Yeah.
When do we want to not set measure to 0 grad?
Honestly, like if you're using neural networks, if you train neural networks, almost never.
Okay.
Yeah, that's a little bit again counterintuitive for PyTorch. It's kind of other libraries, they might not do that. So for example, I think TensorFlow doesn't do that, but it's a little bit counterintuitive here at PyTorch. Yeah. Yes. Yes, that's yeah. If yeah, so again, yeah, if you are using it, for example, you have two different loops. You have, for example, one loop for your like batches. You want to add the gradients. Okay, so that's like one kind of scenario that it might be useful. Okay. So okay. So this is the logic. So this is the logic. We use a logistic regression, but you will see that the neural network is going to be the same thing. The only difference is that our WNB is going to be a neural network model. So let's see how we can do it. So first of all, I'm going to use GPU because I'm going to use neural network. One thing that is making our life easier is to create a variable and store the device there, okay? So then every time instead of just I don't know, CUDA0, I'll just say .to device. So usually what we do is we use an if loop. So we see if the GPU is available, we're gonna do it on GPU. If not available, we're gonna do it on CPU. And then I'm just gonna create this like tensors. Just to show you that you should not add two tensors on different devices, I'm gonna do it here and get an error. So you see one device is on CPU, the other device on GPU. I'm gonna move the first tensor on the GPU, and then I'm gonna multiply them. So you see you get this error a lot, trust me. So this error means you haven't moved one of your tensors to GPU, okay? So use .to device, move everything. And again, if you're, for example, using a neural net, both your model and also your tensor should be on the GPU, okay? So you see here, for example, now I moved it to GPU and now everything is on GPU. So now let's do what we're all here for, the neural networks. So first of all, I create these kind of values. We're going to use them later. So just need batch size, I need the dimension of the input and everything. So I put them here to use later. And again, torch summary is useful for, like I talked about it earlier, it's just useful for seeing how the model architecture will look like. And now I'm going to create a very simple neural network model. How can I do that? I can use an object called nn.sequential, okay? So nn.sequential, I imported like torch.nn as nn. So then I can use nn for it. So nn.sequential is basically stacking these layers together, okay? So here I have a linear layer, then I have a sigmoid, then I have a linear layer, okay? So this is not a deep model. Basically, it has just an input layer, a sigmoid, and an output layer. And then I can just move it to the device and use torch summary to print it. So you see my model has a linear layer, which has like 150, I think, parameters there, 150, sorry, 150 outputs there. And then my second linear model has 200 as the output. And these are the total number of the parameters that I'm having. And again, port summary is very useful because it also tells you how large your model is in terms of the memory. The other way, the alternative way to do it, which is kind of more used because these days models are getting larger, is to define a class that inherits from nn.module, okay? So if you do that, because since the class is inheriting from nn.module, you should follow how like it's kind of created. So you should have an init function like that. So dash dash init dash dash, and also forward, which is like this. So if you create this class, if it's inheriting from nn.module, it automatically tells PyTorch that, okay, here I have a class. You should initialize it like this. So basically in initialization, we are defining the architecture. So we have a base layer, like the input layer, and then we have an output or like the head. And then I also have this forward pass, which tells me how the calculation is being done. So for example, I have a linear layer, then I pass it through a sigmoid, then I pass it through another layer. And this is how everything will look like. So there are two ways to do that. Now, as the final part of today's tutorial, let's apply it on a data set, okay? This data set called MNIST data set, they're just like handwritten like letters. If you've seen your fourth assignment, which I think is released, you're gonna work with another data set called Fashion MNIST, which is very close to this one. So we have 10 classes we're trying to see based on the image. Which class does this belong to? Is it a 0 or 1 or like 9, whatever? So to do that, I'm gonna train a neural network. Let's see what happened. Oops. Okay. So I'm going to import these kind of data sets using like scikit-learn, and then I'm going to create my neural network class. Okay. So again, as I said, I should, if I define it using the nn.module class, I should have an init function and a forward function. So the init function, I define the architecture there. So we can see how my architecture looks like here. I have a linear input layer. I pass it through a ReLU. Then I have a hidden layer that passed like the output through that. Then I pass the output of the hidden layer through a ReLU. Then I pass it through a linear layer, the final linear layer. And then I pass everything through softmax because I have multi-class classification. So the output of the softmax gives me the probability of the image belonging to each of the 9 classes. Okay, so how are the dimensions look like? So I have number of features as my like input dimension. So what are the number of features in an image? They are different pixels of the image. Okay, so if I have, I don't know, 10 by 10 image, I'm gonna have 1000, 10 by 10, yeah. Yeah, I have 100, sorry. If I have a 10 by 10 image, I have 100 like features, 100 pixels. And then the hidden dimension, it is up to you defining the size for it. And finally, I need to have 10 numbers as my output, which are the probability of the image belonging to each of the classes. So this is how my model looks like. And the training loop is exactly the same that I described. The only difference is that I initialize my model like this. So instead of me creating W and B and creating like the logistic regression function, I created the model, the neural network. I create an instance from this neural network. So what I need to do here, I need to define the number of features and the number of classes. You can change it. So here I also can change the hidden dimension, but by default it's 256. And then what I can do here is after I kind of created the model or like initialize the model, I can move it to my device, okay? So my device is GPU. Again, if your input is not on GPU, but your model is on GPU or vice versa, it's not gonna work because your model is basically doing the calculations. Then I do the training loop using the cross entropy loss because I have like a multi-class classification here. And I use Adam optimizer. Adam is basically an adaptive learning rate function. So here is the important part. So what are the parameters of my neural network? I don't know because I have like around like 1,000, like 100,000 parameters. I cannot define them here like W and B. So what I can do is I can input model.parameters as my input to this optimizer. So by default, if I change my model, it automatically changes the parameters because it is the list of all trainable model parameters. And then the training is the same thing. So I compute the forward pass using model xtrain. Then I find the loss function. I also append the loss function to just visualize it. I reset the gradients. I calculate the gradients. And then I'm going to apply the optimizing step. And finally, this is how it looks like. And let's see what is the accuracy. So I get an accuracy of 97.77, which is not that strange on MNIST because it's a very simple data set. And this is how my loss looks like. And I really like this because it goes down and it kind of stays the same. So it kind of shows me that if I do it for maybe 100 more epochs, I won't get that much of improvement. So yeah, that was it for today's tutorial. So